Hey guys, welcome to lecture 7 of this RISC-V processor design course. Today we're going to talk about two very important things which are important both on a performance level but also from a functionality perspective. And those things are called data hazards and operand forwarding, which is the fix to data hazards. And theory on data hazards is extremely rich here as we try to categorize everything. There's really one kind of data hazard that we're going to focus on, which is called a true dependency. And whenever we're talking about data hazard, we really mean read after write hazards, and we'll see how to solve it with operand forwarding, at least with this very simple pipeline that we have. So what is a read after write issue, a read after write hazard? Suppose that we have an instruction coming into our pipeline that writes to any of the 32 general purpose registers, which we'll call RD. Another instruction comes right after with source register RD. What value does the second instruction read from RD? And here's an example. So this add writes to X3 and the second add reads from X3. So what is the value that X3 has when I2 comes into the picture? Let's analyze the pipeline perspective, what the pipeline sees. So at T0, I1 enters the IDU1 stage, reads the operand from the register file, while ID2 enters the IDU0 stage. The next clock cycle, I1 enters the EX stage, I2 enters the IDU1 stage, reads the operand, and here's the issue. I1 hasn't written to the destination register yet, so I2 reads the old value of X3. So this is basically what a read after write means, that a subsequent earlier instruction reads the old value of the register because a previous instruction hasn't executed yet, so hasn't committed the result to the microarchitectural state. How do we modify the code to make sure that this thing works? We need to add no-ops, bubbles, so operations that don't do nothing but basically space the two instructions by 2 clock cycles. At this point, from the pipeline perspective, I1 enters IDU1 stage, I4, which is the meaningful instruction, is still out there in the instruction memory. I1 then enters the EX stage, I4 enters IFU, I1 enters in write back, I4 enters IDU0 stage, I1 completes write back because remember we have flops in the register file, so we have to wait 1 clock cycle before whatever we write there becomes microarchitecturally visible, and I4 enters IDU1 stage, gets the correct value, and now we are correctly executing that sequence of instruction. But can we do better than that? Because we lost 2 clock cycles to fix this thing. Why wait for I1 to complete write back, so for the result to be microarchitecturally visible inside the register file, to use the result while it's there? So how do we fix the read after write without taking a hit in this particular case from a performance perspective? In IDU1, before sending the operands to the ALU, let's check if the destination register of the instruction in EXU matches any source register of the instruction IDU1. And if so, bypass forward. There's 1,000 different ways where in industry you can find this thing, but basically forward the result from EXU to the output of IDU1 or to the input of EXU, because it's pretty much the same thing. So let's see the code, what it looks like. If we go on IDU1, we have this write back to EXU forwarding. And as you can see here, we are matching the EXU write-back address with whatever comes out of this flop, and especially the RS1 and RS2 address. And if it matches, do not take whatever we fetched from the register file, but forward the output of the previous instruction. And if we do so, what happens is we still have an issue because we gained one clock cycle, but if we have back-to-back instruction, it's still gonna fail because remember, we have an output flop on IDU1 and an output flop on the EXU. So we need to take into account those two no-ops, those two bubbles that would have been there if we hadn't had those flops. So what we have to do is we have to do basically the same thing before the flop and add operand forwarding before going through the IDU1 output flop. So this is what happens here. If we go here, you can see that I've added this extra forwarding path right after we fetch the operands from the register file. So from a pipeline perspective, this is what it looks like. So we modified that simple pipeline that we had originally with a few other things. So these are ALU write-back, IDU1, EXU. Those are the flops, okay? And what happens is that at the output, here we are muxing between potential multiple execution unit, like ALU, load and store. For now, we just have an ALU. We send it back to the register file, but also we send it to these muxes here. So we can bypass the register file and take directly the output from the mux. So let's take a look at some tests that exercise that thing. So you can see here we have a pseudo instruction, which is an LI, load immediate. We can take a look at what this instruction looks like when it gets expanded by the compiler. So here we have a test. So you can see that LI gets expanded to an LUI and an add I. And you can see that this triggers a read after write dependency because they both, the first instruction writes to RA and the second instruction reads from RA. So this one goes and tests, this first instruction goes ahead and tests like back-to-back instructions, and these other sequence tests instructions that are spaced by one instruction, okay? Dependent instructions that are spaced by one instruction. This could have been any other operation that didn't use the X1 register. For simplicity, I put a NOP in here. And we can run this test, which is called basic forwarding. And we can see that the test correctly passes, and we can see the RTL log. And here we are executing the LUI. Here we are executing the subsequent add. And here we are executing this add immediate here to X0. We are adding 2. Here we have a no op. And here we are writing add I, X2, X1, 1, which previously was 2, so we're writing 3. Okay, so these basically tests the forwarding. What I did in this simulation, I created a small set of tests that go and exercise whatever we made so far. And here we have a few test cases that we have inside this smoke test list. And if we run the smoke test list, you can see that all test passes, and we are now ready to move forward and go ahead and implement much more instructions, much more complex pipelines, and so on and so forth. So this was a kind of a brief lecture on what operand forwarding is, and we're going to see in the coming lectures that basically data hazards are caused by dependencies, true dependencies between instructions, and we can fix them, we saw with bubbles, but this is not really an option because the compiler needs to do it, because in general we are running compile code. So the compiler is not necessarily aware of the pipeline architecture. So the bubbles are typically used in architecture where the compiler plays a much significant role in scheduling the instructions, like in DSPs and very long instruction word architectures. And I have an entire course on how to build a tightly coupled compiler to the hardware. We saw operand forwarding for simple cases like the ALU that we saw here, but more generally, there will be times where there's no other solution than to stall the pipeline, to wait for the results of an instruction. And this is typically done in more complex cases where we have variable length algorithms like the divider, or where we have not necessarily single clock cycle units like the multiplier that we're going to see in the next lecture. So next lecture, we're going to see pipeline stalls, how we integrate the multiplier and the divider inside our architecture, and start building some momentum here in wrapping up this core. All right, guys, I'll see you in the next lecture.